Hello, my name is Thomas Schwetz from Karlsruhe Institute of Technology, and I will present here a work done in collaboration with Miguel Escudero and Jorge Terol Calvo, where we work out a specific model which allows to introduce large neutrino masses consistent with bounds from cosmology. So in the standard scenario, we have the three standard model neutrinos, and from neutrino oscillations, the mass square differences of these states are known very accurately, and we have these two possible mass orderings, normal and inverted. But from oscillations, we have no information on the absolute scale, and so we need different observables. And I've shown here cosmology, which is sensitive to the sum of neutrino masses, and beta decay, which is a different combination of parameters. And in the standard scenario, exists a one-to-one relation, correlation between these two observables, depending on the neutrino mass ordering. So what we're seeing here is that the Katrin experiment is sensitive to the quasi-degenerate region, whereas cosmological bounds are really very strong, going deep here in the hierarchical spectrum. So indeed, from the oscillation data, we have minimal values, predicted minimal values for inverted ordering and normal ordering, which are in this range, roughly 0.1 for inverted and 0.06 for normal ordering. And Planck CMB plus BIO bound is close to this minimal value for inverted ordering, whereas more recent bounds, for instance here, that they're bound from DAISY combined with CMB, is already below the inverted ordering at 95% confidence level. So we are really approaching the situation that there might be some tension between cosmology and terrestrial experiments, which is illustrated here. We show the posterior distribution for the sum of neutrino masses from cosmology, and then in brown from oscillation experiments. And we're seeing that there is some tension emerging here. This is quantified here on the right-hand side. For current data, we are already facing some tension at the level of 2 sigma, which is probably not dramatic, but it's something to be worried about since at some point, because the posterior distribution is peaking at 0. Now, what may happen in the future, so this is a predictor, if the sensitivity of future cosmological surveys reaches a sensitivity of 0.02 and the best fit remains at 0, we are really facing severe tension at the level of 3 sigma for normal and up to 5 sigma for inverted ordering. Instead, this would be what we would expect if everything is as expected, that cosmology peaks at a finite value, establishes a finite value of neutrino mass, and then this would be consistent. So in this talk, I want to address precisely this question: what happens if limits from cosmology get stronger and stronger and do not find a value? So we need to invoke how to reconcile this data, or even the situation when experiments like Katrin start to see something. Can we relax cosmological bounds to that level that this may become consistent? So there are a number of ideas which have been discussed in the literature. This is certainly incomplete, but I assume that some of these ideas will be discussed in this conference. I will focus on this particular scenario in my talk, which is kind of similar to this famous neutrinoless universe, which was introduced by Beacom, Bell, and Dodelson 20 years ago, and revised by Farsan and Hannestad in some slightly modified versions. And so what is the main idea? This is this Farsan-Hannestad mechanism. So the idea is to relax the bound on the sum of the neutrino mass by reducing the number density of neutrinos. So if the number density is lower than the number density predicted in the standard model, then this bound will become relaxed accordingly. But of course, we have to worry about dark radiation. So the idea to do is to convert standard model neutrinos into some massless particles between neutrino decoupling and recombination. And this allows to keep an effective, the relativistic degrees of freedom, approximately 3 during BBN. So there we have just the standard scenario. Then after BBN, we convert neutrinos to dark radiation, but the sum remains 3. So we still have effective number of degrees of freedom during recombination, and we can satisfy the bounds on N effective. So this is the main idea how this works. So we are introducing a number of massless fermions, which we call chi, and then this a mediator particle which couples these massless particles to active neutrinos. And so we have this scenario. Here is neutrino decoupling, and then between neutrino decoupling and recombination, the dark sector comes in thermal equilibrium, which reduces the number of active neutrino and populates the massless fermions while keeping the total amount of relativistic degrees of freedom as in the standard model. So we can satisfy an effective constraints from CMB, and we are fine with BBN, and we have reduced the number density of active neutrinos. And in this way, we can relax the bound, and this effect is proportional to the degrees of freedom of massless particles which we populate. So here, G chi is the internal degrees of freedom, and N chi is the number of generations. And we see the larger we make this number, the more we can relax the upper bound. So let's focus, for instance, on the yellow curve here. This would correspond to a sum of neutrinos of about 0.6, which is approximately the sensitivity limit of Catherine. And we see to satisfy current bounds from Planck, BIO, we need approximately 10 massless states. If cosmological limits would improve to the value of 0.02, we would need of order 40 to 50 massless states to accommodate such a value for neutrino mass. Okay, now in our paper, we have implemented this mechanism and proposed a simple model to realize this scenario. So what are the ingredients? We add 2 heavy right-handed neutrinos. This is the standard type 1 seesaw mechanism, which will give mass to the neutrinos. We postulate an abelian symmetry, U1 symmetry, and scalar, which is charged under the symmetry to break the symmetry. And then we have a set of massless fermions, and chi is the number of generations of massless fermions which are charged under this abelian symmetry. Now, we can build the following Yukawa sector. So we have here the usual seesaw mechanism, the right-handed neutrino mass, and here we have the light degrees of freedom coupled to the scalar. And once the scalar gets a VEF and the Higgs gets a VEF, we are introducing a mass matrix which takes this particular form. And we are assuming a certain hierarchy among the entries in this matrix. In particular, this quantity lambda is related to the VEF of the U1 symmetry, whereas MD is the Dirac mass related to the electroweak VEF. And so we are assuming this hierarchy here, and then we have the right-handed neutrinos. And so then we can diagonalize this matrix. We obtain heavy states, the active neutrinos, get their mass by the usual seesaw formula. And then we have the massless states. So you see immediately the rank of this matrix implies that we have massless states. And the mixing of the massless states with the active neutrinos is controlled by the ratio of these two quantities, which is a small number according to our assumed hierarchy of the states here. Then we have the gauge sector. We assume that the U1 symmetry is a gauge symmetry. We will get a vector boson Z prime after the symmetry breaking, which couples to the chi particles to the massless states, and the couplings of the Z prime to the standard model neutrinos is induced by the mixing. So we have the direct coupling to the massless chi's. The off-diagonal coupling is suppressed by 1 power of the mixing, and the neutrino-neutrino Z prime interactions as a square of the mixing. Now, this is a relatively simple model. The independent parameter for phenomenology can be chosen to be these 5 parameters from the Yukawa sector, neutrino masses, and one mixing angle, and then the VEF and the mass of the Z prime can be chosen as the relevant parameters. Now I will discuss the parameter space, which is available where this mechanism can implement it. And indeed, it turns out that we obtain a closed region in parameter space. I show here the plane of the Z prime mass and the VEF, the U1 symmetry breaking VEF. And we are obtaining an allowed region in white, which is closed from all sides, which is a definite nice prediction of the model. So let me briefly go through these constraints. First of all, we need to make sure that the dark sector gets thermalized. So the interaction needs to be strong enough. So this region here, where the interaction is very weak, is excluded. So we have to be to the left of this orange region to populate the dark sector. But then we have to avoid that the dark sector gets thermalized before BBN. So this excludes the blue region here to make sure that all the massless particles get only populated after BBN. And so furthermore, we have to avoid that the dark radiation gets strongly coupled around recombination. We know that the dark radiation has to be free streaming, and this excludes the green region here, which completely closes the parameter space. And okay, the scale here is in the few keV, starting from 1 keV to 100 keV is roughly the scale. And this is determined by the requirement that this equilibration happens between decoupling and recombination. Okay, what about the mixing? We also have some constraints on the mixing of active neutrinos with the massless states. Again, we have to avoid thermalization of the massless chi states prior to neutrino decoupling. Here, we have to take into account the effective potential, which is induced by the gauge interactions here. And so we see here that if the interaction is strong enough, actually the equilibration is prevented by the effective potential in matter. And so this allows this region of parameter space, but if the coupling becomes too small, we start populating the massless states. And this puts an allowed range on the mixing. So this was the default range I've shown before, mixing of 10 to the minus 3. If you make the mixing too small, the region closes here simply because we are not populating the massless states efficiently enough. If we make it too large, then we become excluded by these neutrino chi transitions, and the region again disappears at a mixing of about 10 to the minus 1. And again, it's nice that we obtain a closed region of parameter space. Of course, mixing can be very small. which is untestable. But if it's on the upper range here, this is potentially testable in neutrino oscillation experiment, which is something we are working on at the moment to have here some possible tests of the model. Some comments on the right-handed neutrinos. We have only a relatively weak upper bound on the right-handed neutrino mass, which comes just from the perturbativity of this Yukawa coupling. There is also some bound coming from loop-induced Higgs portal couplings, but this bound is relatively weak. One comment on leptogenesis. So here we can do thermal leptogenesis if the decay of the right-handed neutrinos into standard model Higgs and leptons dominates over the decay into the dark sector. Of course, if this decay dominates, then we cannot do leptogenesis. So this region is indicated by the purple band. So here leptogenesis works. If we are outside of this band, actually we have to avoid this decay by making sure that the reheating temperature is less than the right-handed neutrinos, so that these neutrinos do not become populated, because otherwise they would excite the dark sector, which would rule out the model. There is a possible signature in supernova neutrinos. I mean, current bounds from the cooling argument in supernova 1987 are too weak. Actually, they are weaker than PBN, so they are somewhere here. So they are not providing additional constraints. But there could be a possible signal from the Z prime decay into neutrinos. The Z prime escapes the supernova and then decays into neutrinos. And this could lead to a signature in future neutrino detectors, which is probing part of this parameter range. Okay, let me summarize. We have presented a simple model which allows to make large neutrino masses consistent with cosmology. It features a dark gauge symmetry with a typical scale in the keV range with very small couplings to active neutrinos. There are possible signatures in supernova observations, potentially in neutrino oscillation experiments, and right now we are investigating whether this can be also reconciled with a dark matter candidate, which is still work in progress, but the future investigations. Okay, thank you very much for your attention.